Chapter 34 of University Physics discusses geometric optics, where light rays are utilized to understand how images are formed with different kinds of mirrors and lenses. For Lecture 38, we discuss the basics of image formation from light rays, as well as how they are made using plane mirrors. Here are the objectives for the lecture. You may pause the video if you wish. The focus of today will be on just the plane mirror. On the next lesson will be on spherical mirrors. Whenever you bring an object close to a mirror, or some form of glass or reflective surface, you can see a visual copy of that object due to light bouncing off the glass or bouncing off that surface. In discussing this phenomenon, we explicitly define terms so they won't come off as confusing. To start, an object is practically anything which light rays can come from. These rays can be radiated by the object or light source, as you can see in the three pictures on the left, an incandescent light bulb, a bonfire, or a halogen lamp. Or they can just be reflected by the object from some other source. So it can be that any everyday object that you can see. Point objects have no physical extent. They're similar to the simplifications we've made so far to pretty much anything that has mass in mechanics. These point objects would emanate light rays radially, which indicates that we can see these things at all angles given that there are no obstacles. So that's what you can see on the right. So it's just more than one light ray. We've drawn a few of these. In real life, objects would be made out of multiple points. In geometric optics, they are called extended objects. Images would be a point or a set of points at which outgoing rays would converge. These rays are formed when the light rays from an object strike a reflecting or refracting boundary, such as glass. We can see that the images are formed or can be formed even in water, as seen in these pictures. It doesn't necessarily have to be glass, as most surfaces that are transparent or translucent can actually have images reflected from them. Images are also classified whether they are real or virtual. Before we discuss the difference, we note that objects would radiate multiple rays. So at point Q, maybe the tip of the extended object, it radiates two rays. It radiates more than two, but then for the purposes of determining where the image is, two would suffice. These rays would travel differently from one another and would bounce off mirrors differently as well. So the higher ray would bounce off at this point in the mirror, and the lower ray would bounce off at this point. And eventually, these rays would converge at another location again. So not just the two rays, but all of the other rays coming from the tip of the object at some point. And this location is where we would find our image. And for this diagram, that image location is at Q prime. Real images are where the outgoing rays, or rays that travel after hitting the reflective boundary. So to make the distinction, these two rays at the start are incoming rays because they're just approaching the mirror, and after they bounce off the mirror, these two rays would you would call the outgoing rays. Eventually those two outgoing rays would meet at Q prime, and since these rays actually hit Q prime, they're called, well, the image that is formed at Q prime is called a real image. Virtual images occur when the outgoing rays do not actually pass through the image point. If you look at the diagram, the outgoing rays, so again, incoming rays would be going to the reflective boundary, outgoing rays would actually be after it hits the boundary. If you look at the image on the left, you notice that the outgoing rays don't seem to actually converge after hitting the mirror. They'd actually diverge. Despite this, we know that images are formed behind the mirror. If you look at the mirror, you'd see a copycat image. So we can resolve this inconsistency if we extend the outgoing rays backward, or the reverse direction of the ray. In the picture on the left, they would be these dashed lines. Okay? And then we will see these extensions, which we call sight lines, converge behind the mirror. And this is where we will see the virtual image. Note that it is the sight lines that converge and not the actual outgoing rays, which is why we call this image from behind the mirror virtual images. On the picture on the right, you also see the same situation, even though the configuration is different. The object will be on the left side, and then when it hits the boundary, it will actually refract. So this will be in terms of refraction, not reflection. the outgoing rays actually refract away, so they won't really converge at some point to the right. But then if you draw the sight lines, if you reverse the direction, as you can see in the dashed lines, they will converge at a point P prime. So you still form an image at the same side as the object, but it's not going to be a real image. Now let's put these images side by side. Again, real images are formed by actual light rays. The picture on the left shows that the boundary is a window and that the light rays travel through it. We can see a real image because the outgoing rays coming from the left converge at our eyes. Virtual images, on the other hand, are formed by sightlines or dashed lines. Light rays won't really be formed behind the mirror, since the outgoing rays would be reflected off. But the sightlines trick our eyes into thinking that there is a candle behind the mirror, but then that's just the virtual image. Part of geometric optics is understanding where these images would form, and these can be done mathematically. As such, it is important to set sign conventions to the distances of objects as well as images. Consider the picture on the left. There is an object at point P which throws incoming rays towards the mirror. Its outgoing rays would bounce off according to the law of reflection, and its sightlines would indicate where its image may be located at point P prime. Object and image distances are dictated or defined relative to the boundary. So you will see later that if S or S prime is equal to 0, that means the image is located at the boundary itself, but then that doesn't really make sense. So let's call the object distance S. It is positive if it lies on the same side as the incoming ray. Image distance S prime, in this case, is negative. This is because the image location P is at the opposite side, where the outgoing ray will go. Remember that sightlines are not really light rays. So in this example, normally, object distance S will always be positive. We usually determine the sign of S prime. S prime is on the right side of the boundary, but the outgoing ray is on the left side of the boundary. Our convention says that if this is the case, S prime should be less than 0. Let's have a second example. We're going to have the object coming from a material with a higher n to a lower n. So think water to air. Object distance would be positive since S and incoming rays would be at the same side. Again, we usually set object distance to always be positive. If we find that the outgoing rays would not converge, as seen in this example, and it's the sightlines that will, we find that the image to still be in the initial material. This means that the image distance S is negative because P prime, where the image is, and the outgoing rays would be at different locations or at different sides of the boundary. As a summary, the signs of the object and image distances would depend on their relative locations to the incoming and outgoing rays respectively. Besides finding where our image is located, mirrors and lenses can also distort the size of the image relative to the object. We call this property the magnification of the image. Let's start with the lateral magnification M. Its equation is intuitive, which is given by M is equal to y prime over y. The object height is y, and the image height, the image that you form, is y prime. Its relation to image and object distances can also be determined by geometry, which we can see in a later slide. And the equation of M relative to distances is given by negative S prime over S. The sign conventions of M are rather simple. M is positive if the orientation of the image is the same as that of the object. We take y greater than 0 if the object is upright. Again, the object is usually has a positive sign. Object height, I mean. M is negative if the image is inverted, or if the orientation of the image is reversed compared to the object. If the absolute value of M is greater than 1, we get a magnified image since y prime would be larger than y. We get reduced images if the size is less than 1. If the image and object sizes are the same, we get an M is equal to 1. It follows then that y prime should be greater than 0 if the image is upright, or oriented the same way as the object. It is negative if the image is flipped. As with our usual distance conventions, S prime is positive or negative, depending on whether the image is real or virtual, respectively. The focus for this short lecture is on images formed by reflection on plane or flat mirrors. Plane mirrors are supposed to produce images that replicate the object, so a lot of symmetry is involved here. Starting with something simple, the image distance should always be exactly negative of the object distance. This means that the image is virtual, which we can see on the graphic on the right. Now, the image location, P', is determined by the sight lines and not the outgoing rays. Owing to symmetry, the object and the image should be equidistant from the mirror. As seen in the picture, all rays originating from P always diverge from P'. If you trace the rays, the outgoing rays. We trace the outgoing rays based on the law of reflection. We're only considering two rays here for now. One that is normal to the boundary, as you can see here, and one that will have an outgoing ray that will hit our eye eventually. Remember that the image location P' is dictated where these two rays will converge again. Since we can see that the two outgoing rays will not converge, we check if their sight lines will. True enough, they will converge behind the mirror, opposite to the side where the outgoing rays travel. Because of this, we confirm that the image distance is negative, and a virtual image is created. From similar triangles, as well as the angles formed by the law of reflection, we can also see that S and S' should be equal. This slide considers an extended object instead of a point object. We note that the image formed by a plane mirror will always be upright because you want some parallelism, or you want it to look identical to your object. It makes sense because plane mirrors are supposed to replicate how the object looks. This means that the object and image heights should be equal. Like the previous slide says, images formed by plane mirrors are virtual, so S' is just negative S. As seen in the diagram on the right, law of reflection and similar triangles are used to justify why the images should be equidistant from the mirror and both have the same heights. So you could see the two similar triangles here as well as here. And checking how the sides are equal, S and S' should be the same, or in distance, or in length. Y and Y' should be the same, and so on and so forth. You may pause the video if you want to check the geometry. If the height of the image is equal to its object, and their distances are negative, we can conclude that M is equal to +1, because M is equal to negative S' over S. This is the characteristic of a plane mirror. What's not as obvious in our equation so far is that the image formed by plane mirrors is reversed back to front. This means that if you do the right-hand rule and you do it in front of a mirror, the image will look like it's doing the left-hand rule. There's chiral symmetry. So let's answer a quick exercise before we finish the lecture. A candle 4.85 cm tall is 39.2 cm to the left of a plane mirror. Where is the image formed by the mirror, and what is the height of this image? So if you were to draw that simple system, let's say that's the boundary, and then we have our object here. And then say that this height is 4.85, we call this point P. And then our distance, our P' should be roughly around here. So imagine that they have the same size. And then this distance is 39.2. Again, it's a plane mirror, it's supposed to replicate how it looks like. So you assume that this is also 39.2. They have the same height, they have the same distance from the mirror. And to answer this question properly, we already know that the image will be replicated. The image should be formed 39.2 cm behind the mirror, but this means that S' should be negative because the outgoing rays will travel in front of the mirror. You'll have to draw sight lines to specify where the image will actually form. Since lateral magnification is +1, we expect that the candle's image should also be 4.85 cm tall. For this problem, the figure shows an overhead view. We're looking at the top side of a room with a plane mirror. At which of the 5 points does the observer at P see the image of the object? Again, plane mirrors are supposed to replicate the objects shown in front of it. It doesn't really matter where P is, what matters is where the object is located and where the image will form. Intuitively, We guess the location of where the image is based on what choice seems most symmetrical to the system. From there, the answer should just be C, or location 3. If you want to be more specific about how we determined it, let's do the eliminations. 5 cannot be the answer, because that would mean that you will have a real image, because the object and the image would be at the same side. Plane mirrors always form virtual images. Since we know that the object and the image will always be equidistant from the boundary, 3 is the only choice left. So that's it for lecture 38. Thank you for listening.